Okay, so first of all, I'd like to thank the organizers for inviting me to give this talk. So the subject of this talk is not really directly related to the subject of the meeting, except for maybe the last part of the talk, as you'll see. What I'm going to tell you about is some work we have done on system which has, in one dimension, which has 3 spin interactions, and there's a transverse field. So this work has been done with several people. Aditi, who was my PhD student, she's now a postdoc in Chalmers University of Technology in Gothenburg, Sweden. Samudra Sur, who is a PhD student right now, but he's going to graduate in a few months. Saurav Nandi, who is a postdoc in Joseph Stefan Institute, Ljubljana. And Arnab Sen, who is a faculty in Indian Association for Cultivation of Science in Kolkata, who was here last week. And the paper appeared in PhysDev B last month. So the outline of the talk is as follows. So first, there's a motivation. So we are really motivated by the transverse field Ising model, which is very well studied and well understood, which has 2 spin interactions. So we basically wanted to see what happens if you extend the 2 spin interaction to 3 spin interactions. So the second part will be about the 3 spin interaction model. It also has a duality, like the transverse field Ising model. And so I'll tell you about the symmetries of the model and the energy spectrum. And then we went to a lot of effort to find the critical exponents at the self-dual point and the universality class. And it's a long story. Then I'll tell you about the distribution of energy level spacing, which basically suggests that the model is not integrable. And then we find that the system has an exponentially large number of zero energy states. And a subset of them are what you can call scarce states. And finally, I'll tell you a little bit about autocorrelation functions near one end of the system, and you'll see that it has kind of anomalous relaxation with time. Okay, so the general motivation is that is the transverse field Ising model, which is a well-known model with duality. And as you know, it's integrable by mapping it to fermions using the Jordan-Wigner transformation. And the self-dual point corresponds to a quantum critical point, separating an ordered from a disordered phase. So we wanted to generalize this to other models which have duality, but which may or may not be integrable. And because they have duality, it would be interesting to study what happens at the self-dual point. Okay, so it turns out that a family of models like that were introduced a very long time ago in the early 80s. And some of these models were studied using mean field theory and series expansions. So these models in general have Ising interactions involving p neighboring sites and a transverse field. And so these are some of the papers. So the transverse field Ising model, which I'll tell you a little bit about just to recollect in the next 2 slides, this corresponds to p equals 2, so interactions between 2 neighboring sites. And then I'll tell you about our model, which is a 3 spin interaction model. So it turns out there are some systems where this model can probably be realized, or at least models similar to this can be realized in triangular configurations, so one-dimensional chain of triangles in optical lattices with 2 atomic species. Okay, so that's the experimental motivation. Okay, so let me now recapitulate what we already know about the model with 2 spin interactions. So I'm going to use x, y, z for simplicity instead of sigma x, sigma y, sigma z. So this is the Hamiltonian, so I'm calling it H2 because it has 2 spin interactions. So it has Ising interaction between the z or neighboring sites, and there's a transverse field along x. So this is a duality, it's well known. So you define a dual lattice. So the points of the dual lattice lie midway between the points of the original lattice, and the duality is defined here. So the tilde defines the spin variables on the dual lattice. So x tilde n plus half is zn, zn plus 1, and vice versa. So the dual Hamiltonian is of this form. So basically you can see that what we have done by this transformation is that we have interchanged these 2 terms. So this is a transformation which takes you from H to 1 by H. You have to be a little careful when you have periodic boundary conditions that this mapping only works for certain constrained sectors. Okay, so now the model that we want to study. So it has 3 spin Ising interactions. So there's a term like Zn, Zn plus 1, Zn plus 2. And then there's a transverse field, which is the same as in the previous model, H multiplying Sn. So you can show that this model also has duality. So in this case, the sites of the dual lattice coincide with the sites of the original lattice. And this is the definition. So x tilde n is Zn minus 1, Zn, Zn plus 1, and vice versa. So the dual Hamiltonian takes this form. So again, it maps effectively H to 1 by H. Okay, so what are the symmetries of this model? So this is basically a model with 3 sublattices, right? Because it has 3 spin interactions. So it turns out that there are 3 Z2 valued operators which commute with this Hamiltonian. So what these operators are the following. So you take a D1, which is the product of all the x variables on 2 of the sublattices. Okay, so product over j, x3j minus 2, x3j minus 1. Similarly, you can take a product D2 which runs over, so maybe this runs over the sublattices A and B, this runs over B and C, this runs over A and C. So these are all Z2 variables. You can check that these commute with this Hamiltonian. Now, these 3 are not independent of each other. The product of these 3 is identity matrix. So if you just consider 2 of them, the system has a Z2 by Z2 cross Z2 symmetry because each of them has eigenvalues plus or minus 1. Okay, so now given the fact that there are 2 commuting and conserved Z2 operators, the states of the system lie in 4 sectors in which these states are the following combinations of eigenvalues of these operators. There are only 4 because these 3 are not independent. As I said, the product of these 3 has to be 1. So in terms of the system, the states of the system are equally divided between these 4 sectors. Okay, now if you translate by one side, so let's call the translation operator T, that also commutes with the Hamiltonian, it's translation invariant. So you can show that if you do a unitary transformation of these 3 operators D1, D2, D3 by T, then D1 changes to D2, D2 changes to D3, and D3 changes back to D1. Okay, so then you can prove that if you have states with momentum K, then these will come with a 3-fold degeneracy because you can translate them by a certain amount and then that changes the values of D1, D2, D3. Okay, so there's a 3-fold degeneracy of states lying in these 3 sectors. Whereas if there's a state lying in the first sector, 1, 1, 1, all the D1s are 1, there's no degeneracy. There's no particular reason for them to have a degeneracy with any other state. They remain invariant under translations and these Ds. Okay, so the first thing we did is we used exact diagonalization to study this model with periodic boundary conditions. Okay, so let's say this is the data for a system size L equals 27. And you find that there's a dispersion which is gapless at 3 points, k equals 0, 2 pi by 3, and 4 pi by 3. Okay, and this is sitting exactly at the critical point, the self-dual point h equals 1. At these at these gapless points, if you look at the slope, dE by dk, it's about 3.44. So that's the velocity of these low energy modes. Okay, so the next thing, let me show you are the 4 lowest energy levels. So the ground state and the first 3 excited states. So for H less than -1 or more than 1, the ground state is unique and is separated by a gap from the next 3 energy levels which are degenerate. So this comes from what I said earlier, that 3/4 of the state have a degeneracy and 1/4 of the states don't have a degeneracy. Yeah. Yeah, basically because of the duality. Because it's a self-dual point, it maps to itself under duality, and so you expect something special to happen. But I'm going to now give you evidence that it is actually a critical point. That's not obvious just from the duality. Okay, so this is the first proof, that if you look at the 4 lowest energy levels, you find that they're degenerate with each other if your H is between -1 to 1, whereas there's a unique ground state outside that range. So this kind of suggests that there's a symmetry breaking phase transition in H equals plus or minus 1. Okay, now this is of course a small system size 15. The next thing we looked at is the ground state fidelity. So the ground state fidelity is defined as follows. You look at the overlap of the ground state at 2 slightly different values of this transverse field H. And we take the points to be H minus delta H by 2 and H plus delta H by 2, where delta H is quite small. So this overlap, it's well known. It shows a big change when you are very close to a critical point. So these are the data for different system sizes. This is all done with periodic boundary conditions, and we generally take the system size to be a multiple of 3 so that you have this degeneracy with D1, D2, D3 explicitly. Otherwise, that symmetry is really not there. Okay, so when you look at this fidelity, you find that there's a clear dip at h equals 1, and in fact the dip becomes larger and larger. Right now they're all very close to 1, but if you could go to larger system sizes, it will become a larger and larger dip. So this is like the second proof that, or second indication that there's something special which happens at h equals 1. Okay, so the next thing we did is we looked at the critical exponents. So as you know, near a second order quantum phase transitions, various quantities will scale as powers of h minus hc if the system size is very large, or as powers of L if you're sitting exactly at the critical point. So for example, the correlation length will scale as h minus hc to the minus nu, where nu is this correlation length exponent. And if you take some other quantity, it will scale as h minus hc to some power if L is very large, or as L to some power if h is exactly hc. Okay, so first thing we looked at is dynamical critical exponent, z. So here we are sitting exactly at h equals 1, and then we look at this gap between the ground state and the first excited state, which is threefold degenerate. We looked at that gap, let me call that delta E, and we see how it scales with the system size. Okay, so see, we are sitting exactly at the critical point. So this is the scaling, and you find that z is about 1.027. So we take that as z equals 1. So the dynamically critical exponent seems to be 1. So the fact that the z is close to 1 suggests that the low energy sector of this critical point is Lorentz invariant. Okay, and therefore, since we are in one space, one time dimension, the system should be described by some conformal field theory at the critical point, and that's characterized by a central charge C. So the next thing to look at is the value of C. So there are different ways of finding this. One is if you can look at the entanglement entropy between two subsystems of length L, small l, and capital L minus small l. So basically divide the system into two parts and look at the entanglement entropy between them. And there is this formula, I forgot to put in an expression here, is by Cardy, that the entanglement entropy behaves in this way as a function of capital L and small l. The coefficient in front is c by 3, so that's how we can determine c. There's plus some constant c prime which you can find, but it's not important. That's not, c prime is not universal, but c is universal for a particular theory. So if you look at this as a function of small l, plotted as a function of log of this quantity, so this quantity inside the brackets is what I'm calling g of l, this gives c close to 1. Other way of finding the central charge is to look at the ground state energy and see how it scales with the system size. So the first term will of course be proportional to the system size, that's just an extensive quantity, so it will be some alpha times L, minus the correction turns out, the next term after that is proportional to 1 over L, and it depends on the velocity that I told you about earlier, and the central charge, okay, and so this is a kind of universal formula. So looking at this, you can figure out what C is, and you find from this calculation that C is about 0.959. So the two pieces of data, the entanglement entropy and the finite size scaling on the ground state, are both indicating that C is very close to 1. Okay, so the next thing we look at is the magnetization, or the magnetization exponent. Now because the system has a 3 sublattice structure, it makes sense to define 3 sublattice order parameters. So what we do is that we just take the sum over Z for all the sites on the A sublattice, divided by the number of sites on the A sublattice, and you can do the same over sites of the B sublattice and sites of the C sublattice. So these are the sublattice order parameters, and then you combine all of them. So you take MA squared plus MB squared plus MC squared, the ground state expectation value of that, and then square root of the entire thing. Okay, so then you study what happens to that how does it scale with the system size if you're sitting exactly at the critical point h equals 1. Yeah. That is the most symmetric way of doing it. So you might ask, why not just take the sum of all the 3, right? So it turns out that actually somehow doesn't scale too well. I mean, we tried that. So this thing actually does better. Eventually it doesn't matter. For large L, they'll scale in the same way, but this one shows a better behavior. So it turns out that the scaling with L actually involves 2 exponents, the magnetization exponent beta and the correlation length exponent nu, which I have not yet found. told you what it is. So, but this thing just shows you the ratio beta by nu, and we find that it's around 0.129. Now, 0.129 is not very far from 1/8, which is the value of beta by nu that you have for the transverse field Ising model. Next thing we looked at is the susceptibility exponent gamma. So for that you add a longitudinal field Hz, and then you look at how, so that produces a magnetization. You're sitting exactly at the critical point, H equals Hc, which is 1. And so this produces a magnetization, so the derivative of that with respect to Hz gives you the susceptibility. And you know that this scales is L to the power gamma by nu. So this is the susceptibility exponent gamma. But once again, what you actually get from this is just the ratio gamma by nu. So from these plots, you find that gamma by nu is around 1.788. Again, very close to 1.74 or 7 by 4. 1.75, which is 7 by 4, which is the value that you get for the transverse field Ising model. Okay, so the facts that Z is 1, C is 1, and beta by nu and gamma by nu are close to these numbers, which are exactly the same values as for the transverse field Ising model. So they suggest that the critical point of this 3-spin model that we are studying, it lies on what's called the Ashkin-Taylor line of critical models, which exhibit weak universality. So this is an interesting concept, which I had no clue about before we started doing this work, but Arnab Sen, one of our collaborators, is an expert on this. So weak universality is a phenomena where you have a whole line of critical points, so that the critical exponents individually, they vary along that line, but the ratios of critical exponents are the same everywhere on that line. Okay, and this is possible, it turns out, when you have conformal field theories with C equals 1, because they have a marginal operator. And so this, as you vary the coefficient of this marginal operator, it takes you along the line of critical points. And on this line, these exponents separately can vary continuously, but the ratios don't change along the line. So that's weak universality. So at the transverse field Ising model, nu is 1, but we'll see what nu is here. Okay, so we decided to study the Ashkin-Taylor line. So this is described by a Hamiltonian of this form. Now the way I've written this is sitting exactly at a critical point. Otherwise, you'll also have a H appearing in some of these terms. But I've taken the H equals 1 straight away. But you see there's one parameter which you can vary, which is this lambda. So every site in this Hamiltonian has 2 spin half degrees of freedom, sigma and tau. Okay, so you can see that if lambda is 0, then you basically have 2 decoupled transverse field Ising models, right? This one plus that, this one plus that. So lambda equal to 0 actually describes 2 copies of the transverse field Ising model, and that's C equals 1, because each transverse field Ising model is C equals half. On the other hand, if lambda is 1, then this actually describes a 4-state Potts model. This may not be totally obvious from here, but it turns out if lambda is 1, then these sigma x, tau x, and sigma x times tau x are exactly on the same footing. So it actually gives you the 4-state Potts model. That one has nu equals 2/3. So there's a general formula known. Given a value of lambda here, what is the correlation length exponent nu? So this is an exact formula that is known. Okay, so to figure out where our 3-spin model lies on this Ashkin-Taylor line, we should determine what nu is, and then we'll be able to figure out what is the value of lambda where we are with our model. Okay, so the next thing to look at is the correlation length exponent. So this can be again found in different ways. So one way, we tried different methods. So it turned out the best method was the following. So you look at the energy gap delta for different system sizes, and you take this derivative with respect to h, and look at its value exactly at the critical point. So this scales as L to the power 1 by nu, and you find that nu is 0.754. Now the transverse field Ising model has nu equals 1, the 4-state Potts model has nu equals 2/3. So this is somewhere in between. Okay, so nu equals 0.754 tells you lambda is 0.827. So transverse field Ising model has lambda equals 0, 4-state Potts model has lambda equals 1. Okay, so we were kind of happy with this for a few months till we started looking at something else. Yeah.
If you put lambda equal to that, you'll be able to relate with your 3-spin interacting transverse field.
That's what I said. So if you take this formula and put in the value of nu that we got, that gives you lambda 0.827. That's exactly what we did.
And the model will become the original one which you started with.
What's the original? I'm saying that at this value of nu, this is the value of lambda that you get in this model. This is not the original Hamiltonian. I'm just saying.
So I'm saying, what's the relation with
there's
that?
There's no simple relation between the original 3-spin model and this one. They're just supposed to be in the same universality class. Okay, so when we looked at another quantity now called the Binder cumulant, which is the following object. So you take this m squared. Okay, so now let me clarify. This is now described in terms of this new Hamiltonian. So we are leaving aside the 3-spin Hamiltonian for the time being and just looking at this Ashkin-Teller line. So there's a sigma variable and a tau variable. So again, we define order parameter which is kind of symmetric between sigma and tau. So sigma squared plus tau squared divided by 1 by L squared. That's definition of L squared. So then you take the ground state expression value of m to the 4 divided by ground state expression value of m squared squared, and then you take this. So the reason the Binder cumulant is defined in this particular way is so that, so this coefficient 2 and minus 1, they're chosen so that on one end, deep in the ordered phase, h equals 1, this is 1. And in the other end, h equals infinity, this is 0. So this is defined in such a way that it goes from 1 to 0. Okay, so this is what we get. So let me show you the different things here. So our model, the 3-spin model, you see that the Binder cumulant goes from 1 to 0, but it's non-monotonic. Okay, very close to the critical point, it actually dips, becomes negative. Lambda equals 1, this is the 4-state Potts model, that's one end of the Ashkin-Teller line. It's also non-monotonic. It's, you have to really blow this region up to see that it's non-monotonic. Becomes negative in a small region. Now lambda equals 0, that is the transverse field Ising model, is definitely monotonic. And lambda 0.8267 is also monotonic. Okay, so you find that the Binder cumulant is non-monotonic both for our model and the Ashkin-Teller model, but is monotonic for these values of lambda, 0 and 0.8267. So this is suggesting that lambda 0.8267 is really not a description of our model. Okay? And we have to do better. Okay. Now this is something which, again, Arnab Sen is an expert at. So it turns out that very close to the 4-state model, there are very significant log corrections. They're both additive and multiplicative log corrections. Yeah.
Okay, this one's working. Why did you say that the non-monotonicity in the Binder cumulant was indicative that they were not in the same universality class? Like,
because the kind of shape of the Binder cumulant is supposed to be indicative of the university class of the model. So if a model has a non-monotonic behavior and a different model has a monotonic behavior, that's an indication that they are not, maybe not the same university class. It's just an indication. So I'll give you better proof now that our 3-spin model is not exactly at lambda equals 0.827, but it's actually at the 4-state Potts model.
Okay.
Okay. So, and you'll see that the reason we were fooled by our exact diagonalization results is that our system sizes were just too small. So we didn't know about the log corrections at that point. Okay, so what we studied then is we use the density matrix renormalization group, which actually allows us to go to much larger system sizes. Except that DMRG works best with open boundary conditions, whereas all our exact diagonalization results were for periodic boundary conditions. Okay, so it turns out that there are very significant log corrections, as I said. So if you look at, for example, the gap at the critical point multiplied by L, it goes as some number A star, which is actually universal, plus some constant divided by log L. So that's an additive log correction. You can also look at the gap as a function of H. So you vary H now times L, and it is a function of this object. And we took these coefficients because they're the appropriate coefficients for the 4-state Potts model. And this A is something called a metric factor, which again depends on where you are on the Ashkin-Teller critical line. So what we find is that the DMRG data for our model is consistent with the 4-state Potts model with lambda equals 1 and A equals 2. Okay, so here's the data. So the first one is looking at the entanglement entropy. So that tells you C is again very close to 1. And then this is data showing you that our model H3 and the Ashkin-Teller, they sort of, they're parallel to each other. So they have exactly the same slope on this log-log plot. And these are two other plots, delta L times H. They all cross at H equals 1. And you can see that you can go to really large system sizes with DMRG. So for the entanglement entropy, we went to 600 sites. For this data, which went up to 390 sites. So much, much bigger than what you can do with exact diagonalization. And this last one is showing that this H3 or 3-spin model and the 4-state Potts model really exactly fall on the same line. Once you put in A equals 2 and then you try exactly this form with these particular powers. Okay.
Sorry, what was delta A?
Delta is the gap, energy gaps, if you're exactly at the critical point H equals 1, between the ground and the first excited state.
I have one more question. Now, because we have this four-state Potts model, all the dynamical exponent and other exponent will be exactly same.
Yeah, so it turns out C is still 1, Z is still 1, but nu is 2/3 at the 4-state Potts model. So the exponents are not the same, the ratios of the exponents are the same. Yeah. Okay, so now let me just give you a very brief sort of qualitative argument of why, on hindsight, we could have anticipated this, why our 3-spin model should fall in the same universality class of the 4-state Potts model, only by hindsight, okay. So the Hamiltonian and the Ashkin-Taylor line is like this, and as I said, it has a Z2 cross Z2 symmetry for all lambda. That just corresponds to flipping sigma x or flipping tau x. But for the 4-state Potts model, it is known that the low energy sector has an enhanced symmetry given by S4, the symmetry permutation group of 4 objects. So why does a symmetry like that appear at the critical point of our 3-spin model? Okay, so here's a qualitative argument. So if you look at this Hamiltonian, our model, in the limit h much less than 1, so deep in the ordered phase, there are actually 4 ground states, which are given as follows. So all the spins can point up, or spins on 2 of the sublattices can point down and 1 can point up. So the 3 sublattice magnetizations can take 4 possible values. Okay? So this tells you that there are actually 4 possible ground states, of course deep in that ordered phase. And this set of order values of the order parameter, they form the corners of a tetrahedron, and the symmetry group of a tetrahedron is the permutation group of 4 objects. So by hindsight, this is kind of the qualitative reason why you might have expected our model to show be in the same universality class as the 4-state Potts model. Okay, so this is all about the critical properties of our model. So maybe I can pause if anyone has questions about that, and then I'll go on to other things. Yeah.
Does it generalize if I had more than 3 Zs?
Right, so good question. So the 4-state Potts, the 4-spin version of this, product of 4 spins, it's sort of undecided. It's probably weakly first order. Okay, but people don't know this. They have not studied that with such large system sizes. It seems to be weakly first order. If you have 5 or more, then it's definitely first order. Okay. That's known from numerics. Okay. You still have the duality. That's why we chose this particular family of models. They all have duality, and so all of them h equals 1 is a special point. Okay, so by the way, you cannot solve this model by Jordan-Wigner because there are 3 of these. So when you try Jordan-Wigner, there's a string left over when you take this product of 3 objects. So they're definitely not solvable by the Jordan-Wigner transformation to fermions. Okay, so the next thing we did is we wanted to know whether this model is integrable or non-integrable. So one of the standard tools for that is to look at the energy level spacing distribution. So this has appeared in some talks earlier. So you look at the nearest neighbor difference between energies, and then you look at this quantity R tilde, which is the ratio of the minimum values and the maximum values of 2 neighboring values of Sn. So we find from our calculations that the average value of R tilde is 0.533, which is very close to what you expect for a Gaussian orthogonal ensemble. So the model appears to be non-integrable. The other thing you find is that the probability distribution of this is in good agreement with, again, Wigner-Dyson distribution for this Gaussian orthogonal ensemble, which is like this. Okay, so here's the data to show you that. Now it's very important when you do energy level spacing distribution is to look at a particular symmetry sector, because you don't want energy levels from different symmetry sectors mixing up with each other. So we looked at 18-site system with open boundary conditions, so there's no translation invariance, and a particular symmetry sector, D1, D2, D3 is 1, -1, -1. Also, we stayed a little bit away from zero energy because something fantastic happens at zero energy that I'll tell you after this. Okay, so this is the plot that is from which we find that the average value of R is 0.533, and this distribution agrees with the Wigner-Dyson distribution that I told you about. Okay, so this is an indication that this model is probably non-integrable. Okay, now about zero energy states. So this model, our model, Hamiltonian, it anti-commutes with this operator, which is a product of all y's, sigma y's. So this implies that the energy levels must appear in plus or minus E pairs. Now, if L is even, turns out we've discovered that there's an enormously large number of zero energy states for any value of H. And the number of such states grows as 1.43 to the L. So this is a numerical plot that we got from exact diagonalization. System size is going up to 16. So the number of zero energy states plotted versus the system size log-log plot gives you this 1.43. So it turns out that this is actually consistent with an index theorem which is described in this paper, which says that the number of zero energy states must grow at least as fast as the square root of the total number of states. So this would be 1.41 something. So this is less than 1.43 as the index theorem says it should be. Now it turns out that zero energy states come in two types. So if you write H3 in this way, so there's the first term which I'll call it as capital Z, the second term I'll call it as capital X. There are type 1 states which satisfy Z size 0 and X size equal to 0. So there are zero eigenstates of both parts of the Hamiltonian simultaneously. Let's call those type 1 states. And then there are type 2 states which are zero energy eigenstates of H3 but not Z and X separately. So type 1 states, as you can see, are very special. There are zero eigenstates of these separately. So they don't even care what the value of H is. So you can vary H in time or you can vary it in any way you like, and these states continue to be zero energy eigenstates. Okay, so for example, this means that if you vary H periodically or quench it or anything, nothing happens to these type 1 states. We also find, sorry? Yeah.
The zero energy states, what are the general kind of
It just needs to have this, this kind of structure that there are, okay. So basically the Hamiltonian has to have a block structure with zeros on the diagonal parts of the blocks and things only on the off diagonal part of the blocks, okay? And then if the Hilbert space dimensions of the two parts, right, corresponding to the two blocks, if they have different dimensions, then the number of zero energy states is guaranteed to be at least as big as the difference of those two Hilbert space dimensions. That's what the Hilbert index theorem tells you. The other thing is that these type 1 states we find have very low entanglement entropy between two halves of the system. So these really qualify as many body scars, and so you get, if you started with a state close to one of these scar states, it would violate ETH. Okay, so first let me show you about this entanglement entropy. So this is a plot of the entanglement entropy, half chain entanglement entropy as a function of E for all energy states. So you find that most of the states fall in this curve, and this curve fall on this region, and this region becomes narrower and narrower as you increase the system size from 12 to 18. But these type 1 states, they all lie at zero energy, and some of them have extremely low entanglement entropy. So these are really the scar states showing up. It turns out that we were analytically able to find some scar states exactly, and this is really quite amazing. We never expected something like this to happen. So it turns out that you take a system, let's say 8 sites, then you form singlets between pairs of sites as shown here. And so you can show that these are type 1 states. They are zero energy eigenstates of both parts of the Hamiltonian simultaneously. Now if you look at how many of these states are, so these are actually what are called, they form a subset of RVB states, resonating valence bond states. And you can see that if this is going to be a scar state, then you can just rotate this by one side and that will give you another scar states. And you can rotate it by L by 2 amount. So that tells you the number of scar states like this grows at least linearly with the system size, okay? So we don't really know how many scar states there are, whether there's an exponentially large number of them or a power law number of them, but it grows at least linearly. We also find that there are scar states involving products of singlets and triplets. I'll finish in a minute. Okay, so this is really kind of amazing that this kind of singlets and triplets show up in scarce states, which has something to do with SU2 symmetry, but our model has no SU2 symmetry in it. The last thing we wanted to tell you is that we looked at autocorrelation functions near one end of the system, and we looked at infinite temperature. So this is a trace of sigma sigma, at 1 at time 0, 1 at time t, summed over all states, and these are the kinds of behaviors you find. So you find these extremely long time oscillations. So this is ZZ autocorrelation. Some of them have extremely long time oscillations. This is the log scale, notice. So some of these oscillations go up to 10 to the power 4 in time, which is much bigger than anything you might expect from the energy scales of the problem. This is the XX correlations. Again, you find these long-term oscillations. And also there's something funny happens at L equals 2. So this is the second site from one end of the system. It actually never goes to 0. It goes to some non-zero value for a very long time. So we don't really understand several things about this. These oscillations we can find in some perturbative limits, h very large or h very small. But at other values of h, intermediate values, we don't really understand why there are these oscillations. Also, we don't understand why they decay at all. Okay, so that probably has to do with transitions to other states, and you have to use Fermi golden rule to understand that. And also this anomalous behavior for L equals 2, we don't understand. Okay, so the summary is we have studied a one-dimensional model with 3 spin Ising interactions and a transverse field. So I've told you about the symmetries of this. It seems to lie in the university class of the 4-state Potts model. Energy level spacing distribution seems to indicate this is non-integrable. It has a large number of zero energy states, subset of which are scarce states. So one problem one question we don't have an answer is how does the number of scarce states grow with system size? And then the autocorrelation functions near one end show anomalous relationship with time, and we don't really understand why this happens. So that's it. So these are the people involved, the reference, and we'd like to thank two people. Hosho Katsura, he is actually the person who made a suggestion which led us to analytical solutions of the scarce states, and Chetan Krishnan, who was involved in the early stages of this work with talking about duality, and funding from these places. Thank you.
Thank you. Thank you for this very nice talk. We have time for a few questions.
So I'm just wondering if you have, instead of p-spin model with a transverse field, then is your degeneracy 2 to the power of p minus 1, and you get, and so you'll get, z2 cross z2 cross z2 p minus 1 of those. For instance, for just a regular transverse field Ising model, you have a single z2. For this, you have two.
No, I don't think it grows like that. It's not
but you will have a duality, I guess.
You always have a duality.
Right.
And I don't offhand remember what the symmetry is.
Right.
I don't think it's just Z2 cross Z2 cross Z2.
Okay, so that's too good to be true.
That's too good.
Right.
To be true.
Right.
But it does have a certain number of discrete symmetries.
Right.
But as I said, if P is equal to 4 or more, it probably have only first order transitions. So you don't have all these fun things with quantum.
Yeah, I'm just wondering if that's also because you can then map it onto a higher P Potts model, and so
yes.
Right. Okay.
Could be related, but I'm not sure.
Right.
Yeah.
And just one last question. Do you understand why the central charge is close to 1, or is 1 in your model?
Not really.
Okay.
Yeah, I mean, that's something we found from our numerical analysis.
Right. Okay.
But it was not obvious to us from the beginning that it would be, central charge equal to 1. In fact, for a long time, we thought that because it has a 3 sublattice structure, maybe it should be the 3-state Potts model,
Right.
which has C equals 4 by 5. But that turned out not to be the case.
Right.
Right. Thank you.
Yeah.
Yeah, just one question about these level spacing statistics and all the diagnostics. So they don't have anything special at the dual point, right? It basically doesn't know anything about the dual point.
So this picture was from H equals 1.
Yeah,
but it doesn't matter. So actually, it doesn't, as I wrote down, the plot does not vary much with H. Of course, if H is much less than 1 or much bigger than 1, it's almost integrable, and then it's not going to be true. But as long as you're not at those extreme points, these levels, it's going to be Gaussian orthogonal ensemble for all values of H in between.
But the autocorrelation, it somehow knew about the dual point, is it? Maybe I'm
The
mixing two
autocorrelation
things.
function, yeah. So autocorrelation function does know about the cell dual point. So these are, so I didn't have time kind of rush through this. So these three plots are for h equals 0.2, 1, and 5. So this is the critical point where it actually oscillates the least. It just goes to 0 very fast. But 0.2 and 5, we took them as h and 1 by h. You can see that it oscillates for much longer. And so these extreme values of h, much less than 1 or much bigger than 1, we understand perturbatively. Okay. But we don't understand what happens around h equals 1.
Thanks.
Your symmetry argument for the number of zero modes, that presumably goes through if you go to larger P, because that only requires the anti-commutation.
No, it doesn't go through. Okay. So this, you need this operator C. We need an operator which anti-commutes with the Hamiltonian. But if you have an even number of z's, it will not anti-commute with y, product of y's, right? Because y anti-commutes with each z. So you need an odd number of z's to appear.
Right.
So
if we do a odd P, for instance,
Yeah.
does that work
Yeah.
generally?
For odd P, it will probably work. P equals 5 will probably work. But we just didn't study that much because it has a first order phase transition. So we are not so interested in that.
Last question. Yeah.
Does this model has an exact strong zero mode?
That was our reason for studying these autocorrelation functions, to figure out whether it has a strong zero mode or not. So I would say that it probably doesn't have a strong zero mode, because eventually these autocorrelation functions are going to 0. And if you had a absolutely strong zero mode, they would not go to 0. They would just remain non-zero up to infinite system size. So basically we studied these to figure out if there's a strong zero mode or not, and the answer seems to be no. Thank you.